if you have reasons to believe that there is a tipping point beyond which it is difficult to return, I think the wise thing to do is go carefully. And it's good to realize that there might be a tipping point. If you are walking blindfolded in a landscape and there is a gentle downward slope, and maybe there is at some point an abyss, and if you fall in, you'll die. I mean, it's interesting to know that whether the abyss exists or not. You would move around more carefully if you know the abyss exists, even if you don't know where it is. I wouldn't call the insight of the existence of a tipping point useless if you don't know where it is.
Welcome to Inside Biodiversity. This podcast is hosted by IDIV, the German Center for Integrative Biodiversity Research. My name is Volker Hahn. I am head of the communications unit at IDIV. My guest today, Professor Marten Scheffer, is a professor at Wageningen University Research with expertise in aquatic ecology. He is also author of the highly acclaimed book Critical Transitions in Nature and Society, and he has co-authored several highly influential papers on the Planetary Boundaries and Safe Operating Spaces framework. In this episode of Inside Biodiversity, we revisit questions I discussed last time with Helmut Hillebrand. How frequent are tipping points in the biosphere? Can they be scaled up to a planetary boundary? And can these concepts guide policy and management? Scheffer and Hillebrand share common ground on some issues, but they disagree on others. Enjoy. Welcome, Marten, to Inside Biodiversity.
Thanks.
So my first question is, why did you study ecology?
Well, as a kid, I was always fascinated by nature, by birds, plants, mushrooms. It ran in the family, so to say. So it was a natural choice for me. Together with studying music, conservatory, I studied also violin, so I couldn't choose between those. But nature was an obvious choice for me. I started out with paleontology, but in the end, I decided on ecology.
So today we'll talk about critical transitions, and you've written a book about that. What made you interested in this topic?
I started out studying at some point theoretical biology. So that's the mathematics of complex systems. I learned about all kinds of interesting phenomena like chaos and cycles and pattern formation, and also alternative stable states, tipping points. So I found that all fascinating. And then I got my first job, and the job was to make lakes clear that had become turbid, and that was for a state research institute. And we understood why the lakes were turbid. That was because they were getting too much nutrient loads, too much pollution. So already the government had started reducing the pollution, and that worked, but the lakes didn't respond. They just stayed turbid. And then some colleagues from England and Denmark, they found out that you could actually flip those lakes to a clear state by a shock therapy. The shock therapy was taking the fish out temporarily, and they would get clear, and then they would stay clear, even if you let the fish back in. And everybody found that like fascinating and puzzling. And I immediately realized that this was actually a good fit for the theory, the mathematical theory that they had taught me at university. And it turned out to be like that. Those lakes have the tendency, the shallow lakes that we have here in Holland have the tendency to be in either of an extreme state, turbid or clear, and when they're in one of those states, they tend to hang on to that state. So that's how I got into the business of tipping points, so to say.
So you've already given one great example of two stable states that are connected, so to say, through a critical transition. Can you define in, let's say, more general terms what critical transitions are?
I have come up myself with the term critical transition because I wanted to get away a bit from tipping points, because there was a lot of confusion about tipping points, what precisely it is. And often in reality, it's very hard to prove precisely what is happening. I wanted to get away from that and came up with the term critical transition. But the definition in the end is like similar to what others would say about the practical definition for tipping points. And that is when you reach a threshold in the environment or in something beyond which the system starts to change, and that change is reinforcing itself. It's self-propagating. So suddenly the change goes faster and faster until it stops in another point. So that's the self-reinforcing feedback. You move from a situation where the old state was kept through self-reinforcing feedbacks to a situation in which you get this accelerating change towards a new state.
So that also applies to shallow lakes, that if they are, let's say, in the turbid state, you have to push them hard so that they would go back into go into a clear state, and vice versa. Is that correct?
Yeah. So when I talk about feedbacks in the lakes, the way it works is that when the water is clear, you have plants growing on the sediment, submerged plants, and those help keeping the water clear in various ways. Now, those plants also need clear water. So if the clarity is lost, they die, and the clarity can become lost because when you get more nutrients, it becomes easier for the phytoplankton, for the microalgae, to grow and make the water turbid. And even though the plants help making it clearer than it would be without plants, they can't stop that completely. So when a critical turbidity is reached, there's just not enough light for the plants anymore, and they start dying. And now you can imagine if the plants die, they don't help making the water clear anymore. So it becomes very rapidly more and more turbid. And then it's very hard to get them back. You can reduce the nutrients, so the microalgae, the phytoplankton grows less. But without the help of the plants themselves, it's not so easy to reach that clarity. So that explains, that's in a nutshell, the story of the shallow lakes.
Yeah. So you've written this book, and there are plenty of other examples from nature and also society where you have identified these critical transitions. Can you give us maybe one or two more examples of critical transitions in the biosphere?
A well-known one is the dieback of coral reefs. You hear a lot about the reefs because of the bleaching. In some areas in the Caribbean, for instance, the reefs have been overgrown by seaweeds. So those are two possible states. It's either a seaweed field or a coral reef. And the only way to keep it a coral reef is that some animals eat the seaweeds. And in the case of the Caribbean reefs, the seaweeds would be eaten by all different kinds of fish and also by sea urchins. Now, two things pressures were on the reef. One is nutrient pollution and runoff from the land. The siltation is bad for the coral, and the nutrients are good for the seaweed, so it becomes easier and easier for the seaweed. The other thing is that there was overfishing, and a lot of the herbivorous fish that would eat the seaweeds were in the end decimated. Now, still, you didn't see an effect because the sea urchins could do the job. It was the last, so to say, that could do that functional job and eat the seaweeds. And the result, of course, is that there was a tremendous amount of sea urchins. They had no competition anymore. And when there is a monoculture, there is a risk that you get a pest in it. And that happened to the sea urchins. They got a disease, they died off massively. And then those seaweeds were released from the pressure and they overgrew the reefs. And it was very difficult to get back from that situation because of, again, several feedback mechanisms that keep that seaweed state stable.
So once you cross a certain threshold, then you have this disproportionate response of the ecosystem.
Yeah. That is actually, I realize now, an example of where you progressively deplete a functional group. So that the functional group, in the sense that they all eat seaweed, and when there is only one left, yeah, that's risky business. So let me give another well-known example that doesn't have to do with loss of biodiversity so much, and that's the tropical rainforest. Tropical rainforest, as the name suggests, needs rain. And if there is not enough rain, the trees die. And that's not a gradual change. When it becomes drier and hotter, that's a bit of the same thing, because then you got more evapotranspiration. You lose the trees that need most rain, but you move a bit to the hardy trees that can resist that condition. But in the end, it's just very hard for a tree at all to suggest, and you lose kind of that functional group, the tree in general, so to say. And what happens in the tropical forest is that you tend to shift to a savanna. And now a savanna is a state that everybody knows. You see the grass with a few isolated trees, and that open state is maintained by fire. And that is because grass is very flammable and it can regrow easily after the fire, but trees don't survive that. So you get a self-reinforcing feedback between grass, the fuel, so to say, and the fire. In a dense tropical rainforest, there is no chance for a fire. It's too wet. There is no grass to burn. But as you cut more and more trees, it becomes drier in the understory, and an open forest is more easily burning. And once it burns, it can go into the savanna state, and then it's very difficult to go back. So already here you hear that there are in fact different factors that affect the resilience of the forest, so to say. The climate can affect it. If it becomes hotter and drier, that's risky business. But also cutting of trees can affect it. So that is important, because it means that if the climate is changing, you can still try to keep the forest resilient by not cutting too many trees. Then it self-protects more easily. So that's the rainforest in a nutshell. Again, much more can be said about
Yeah.
example.
So there are critical transitions in the biosphere. A key question then is, how frequent are they in biology? And in the previous episode of Inside Biodiversity, we had Helmut Hillebrand on the show, and we discussed about, how frequent are disproportionate responses of ecosystems to environmental pressures. And he did a meta-analysis looking at such pressure response relationships. For instance, you would increase temperature in an ecosystem or the nutrient input, and then look, how does the ecosystem respond, for example, productivity. And what they found, I'm citing here, they found that threshold transgressions were rarely detectable. Instead, ecological responses were characterized mostly by progressively increasing magnitude and variance when pressure increased. Is this in line with how you think about critical transitions in the biosphere, or is there some kind of contradiction? What do you think about that?
No, I think I would agree that as a rule, you see gradual change. That is mostly the case. But of course, the cases where you see abrupt change, critical transitions, tipping, they are rare, but they are important. They are meaningful. So they are the exception, but they are potentially very impactful. So it's an interesting exception, so to say.
Yeah, they're impactful because it's hard to get back.
It is hard to get back. So the examples that I mentioned, the lakes, but also the coral reefs and the tropical rainforest, when a coral reef dies off, when the functional group of corals dies off, then with it go a lot of species. So it's a structural change in the system. The same for the tropical rainforest. It's a structural change where you go from, in both cases, from a very biodiverse system to a less diverse system. A savanna has much less species than a tropical rainforest, and the same holds for the coral reefs. If you have a functioning coral reef and you replace it by seaweeds, you gain species, you gain some species, and you lose other species. But in those examples, the gains are relatively less than the losses in numbers of species.
Mm-hmm. So some of these transitions then are undesired, and we would like to prevent them. If we have observed them in nature before, then it's clear there is such a tipping point, and we might be easier to say, well, where are they? Now, what Hillebrand says in terms of policy and management, the concept is useful only if you know in advance where this tipping point is or where this critical transition happens, because you want to prevent it through management. And if you can only retrospectively say that you've crossed it, then he says for management at least, it's rather useless. What do you think of that?
Well, on that point, I would not agree. If you have reasons to believe that there is a tipping point beyond which it is difficult to return, I think the wise thing to do is go carefully, and it's good to realize that there might be a tipping point. I mean, if you are walking blindfolded in a landscape and there is a gentle downward slope, and maybe there is at some point an abyss, and if you fall in, you'll die. I mean, it's interesting to know that whether the abyss exists or not. You would move around more carefully if you know the abyss exists, even if you don't know where it is. I wouldn't call the insight of the existence of a tipping point useless if you don't know where it is.
Yeah, this is also a point that you raise in your book. And you ask the question, well, where is the burden of proof for the existence of a tipping point? So in that case, you would say that because of the, let's say, precautionary principle, it's not necessarily with those scientists that claim that there is a tipping point, correct?
It would be unwise to assume there is no tipping point until you've fallen in the abyss, so to say. I think everybody can see that, I would say. You shouldn't be exaggerating and saying there are tipping points everywhere, but if you have solid evidence that there could well be a tipping point, you just don't know where it is, then that's reason to be extra careful, I would say. And that's also the way. There is also always uncertainty in those large systems. There is less uncertainty in when you do research in an aquarium, but if you do research in the ocean or the rainforest, you never know exactly. That's important because the bigger and therefore the more important the system is, the less scientifically sure you will be of things. And that is for the big biomes, ecosystems in the world. Usually we have to rely on evidence from the past, paleo evidence, to know that such tipping points exist. And it's hard to say precisely where, but yeah, it's useful insight, like the climate tipping points, and those are related, of course. When people talk about climate tipping, the idea is that there are several tipping elements in the climate system. It's not one tipping point for the whole climate system. There are tipping elements, and amongst those tipping elements, there are the rainforests, for instance, because they have an effect on the climate and they are affected by the climate. So you can't really see that apart.
Mm-hmm. Well, you say that uncertainty will always remain, especially with those large and complex systems. But can research help to actually reduce this uncertainty and know better whether there are tipping points, critical transitions on the horizon, and maybe also when they might happen?
Exactly, yeah. That's the whole the whole business we are in. We're trying to reduce the uncertainty we have about it. So if you look at our original paper on planetary boundaries, you'll see that it has the concept, and we were discussing a lot in that group whether it should be related to tipping or not. And in many cases, you don't know whether there is tipping or a threshold or a more gradual response. And in that case, and also if you don't know where it is, what is the safe operating space? The safe operating space is to stay where you know more or less well that you're on the safe side. And the more uncertainty there is, the smaller that safe operating space really is, because you can't be certain. So that whole idea of uncertainty is very much part of the safe operating space concept that we proposed. And then a lot of the research, and you see that especially in climate research, is to try to reduce that uncertainty. For instance, with the thermal haline circulation, are there ways to infer that we are getting close to a tipping point or not? Is there any time scale? And in those systems, there is no silver bullet scientific approach. It's not that you just have to study time series, or you just have to run simulation models or do experiments. You have to piece the evidence together from those different approaches. Evidence from the past, experimental results, time series observations, models, complex models, simple models. And then it's like a detective profession that you have as a scientist to try to figure out, even if you'll never be certain, you're in the business of reducing that uncertainty and knowing better and better.
Mm-hmm. Very interesting. We're already now talking about planetary boundaries, so we've kind of moved from the local scale to the global scale. And one question I have about the planetary boundaries, you mentioned that there is a lot of uncertainty, and that's why sometimes you define those safe operating spaces rather broadly. But isn't there also a danger to that if you do not communicate that openly? People will wonder, well, now we've crossed a boundary. I didn't see anything happen. Were they not honest with us about what they knew about these boundaries?
Yeah, I think the communication is perfectly open. If you read the scientific papers, that is done well. The problem is that to communicate something to a large audience, you sometimes have to simplify, because it's difficult to understand and remember something very complex. And that's tricky. I agree with you that that's a problem if you say, well, there is this particular threshold, and then it doesn't happen. I agree that it is a difficult concept to communicate. Uncertainty is difficult to communicate. People have, in general, difficulties understanding that science always, especially when it is about big complex systems like society, like the climate, like ecosystems, there will always be uncertainty. There will never be certainty. The original idea of the safe operating space is that it is defining what we think is probably safe. And when you leave that zone, you enter the zone of uncertainty. I mean, that's the original idea. So it's not like you enter you reach a certain threshold and then the whole thing collapses. In the original conception that we had of the idea, it is that you are entering an uncertain area in which big things might happen. Yeah.
Yeah, I agree that this is very difficult to communicate. I think those uncertainties are key and important. What I do observe is that many people don't understand that uncertainty. They think there are catastrophic tipping points for sure ahead, and we'll reach it within a couple of years, and then we're doomed.
Yeah, yeah.
And this is probably not what the papers say, but this is how it's understood by many. That's at
Yeah,
least my impression.
yeah. No, I agree. I agree. And that's a matter of poor communication, I would say. And it is something between scientists and journalists like you, because journalists are also seeking clarity and perhaps seeking spectacular statements. And that's not a very good idea. I mean, it, I think there is very little uncertainty about the finding that we are entering like a situation that can have massive changes in the Earth. We can lose a lot of species. We can see climate going into very dangerous realms. Uh, I think there there is little disagreement about that. But simplifying that into a few tipping points, that is also not a good idea. It's like with biodiversity, if you lose species, is there a critical number of species that we need? I think that's very hard to say. Is there a certain biodiversity loss when that loss starts propagating and causing even more loss? That could be one element of cascading extinctions of biodiversity in the far past, so to say, in deep time. And maybe it can happen in plant pollinator systems, but we're quite uncertain about it. We're also quite uncertain about how much biodiversity we need, if we need all those species, what precisely it does. But I think that's distracting the attention from what really matters, and that is that we would like to keep species. We would like to not drive them extinct. We would like to pass on the Earth in a good state to our children and grandchildren. And that's a much better reason to preserve biodiversity, even if the rhino or the giraffe are not very useful for one particular ecosystem service. It would be a good idea to preserve them just from ethical perspective, how you want to pass the planet on, not just for the giraffe and the rhino, but also for our children to enjoy it. That's a whole different discussion, whether you should think from the species perspective or our perspective. In any case, I think that whole discussion about the functional role of biodiversity and tipping in biodiversity is in a way beside the point if you're looking for whether we should preserve biodiversity or not.
Yeah, and I agree. And it's also a case for preserving biodiversity, even if you're below a tipping point or below a boundary, because then you're already changing. We are already drastically changing the environment, and we are losing species, at least on a global level. And it can be worrying way below a boundary. I would like to address one boundary, though, the functional biodiversity integrity boundary. When I look at the examples you give in your book, then it's always on the local level. You look at critical transitions on the local level. Now, here we are scaling this up to a global level. I know that Johan Rockström, the well-known father of the planetary boundary concept, says that there is no scientific evidence for planetary scale tipping behavior for this planetary boundary, functional biodiversity integrity. Then I wonder, is that a useful concept if there is no tipping or there's no evidence for tipping, but we do suggest that there will be disproportionate responses once we've crossed such a boundary? I'm not convinced. What do you think? Like, does this make sense on a global level?
I'm not convinced either. The only counter argument I could imagine is that with mass extinctions in the past, we have seen and those have, what is it, 5 or 6 mass extinctions. There we have seen probably like cascading loss of species, right? We lost all the dinosaurs, all of them, except for some the birds that did well, and it was all replaced by mammals and other things. It's not like we lost some dinosaurs, 50% of the species, and then 40, they were all basically gone. You get a complete reorganization of biodiversity. Good for us, because otherwise we wouldn't have been there probably. There have been moments in the history of evolution when a lot of species disappeared in a very short time. Mostly that has been induced, as far as we know, by climate change. The meteor played a role probably, but the others, it was largely rapid climate change, probably. Perhaps large-scale anoxia of the oceans, killing off all the ocean life almost. So the climate changes that caused those were less rapid than the climate change we're seeing now. So that is an argument that we cannot really exclude, that the current rapidity of climate change, together with the pressure we put on ecosystems, that it could induce some point where you get a cascading extinction. I agree with Johan Rockström that we don't have hard evidence, but we can't entirely exclude it either, I would say.
Mm-hmm. So we've covered a lot of topics. I would like to end on a positive note. In your book, you have described good transitions. So going back from a undesired stable state in an ecosystem back to probably the previous state that is, more desired by us humans. Can you give an example of how we can do that?
Well, the lakes are a very good example because taking out the fish temporarily has helped to recover a lot of lakes. Sometimes it needed to be done later again. It also depends on the pollution. You should do something about the pollution first. So those are our examples. I think the most of the thinking now about positive tipping has to do with positive tipping in human society. Can we tip towards a carbon neutral society? Can we tip from a world dominated by fossil fuel cars to a market dominated by electric cars? So there is a lot of interest in that, and I'm very interested in that. My upcoming book is entirely about that, I would say. It'll be out in February with Cambridge University Press, and it is called Tipping Out of Trouble. And it is basically asking the question whether, as humanity, we will be able to change course in a positive way. It's not like a given that we will do that, but if you look at our past, we have had a lot of positive tippings. We have abandoned slavery, for instance, and we have allowed women to vote. Those are changes that nobody thought beforehand that it would ever happen. And in the hindsight, it's hard to see why it didn't happen earlier. But also, for a long time, we lived under kings and emperors. And then with the Enlightenment thinking, there was doubt whether we should do that. And there was like an argument for democracy and making the world more fair. And that didn't go very well with the ruling order. The book by Baruch Spinoza that he wrote was immediately forbidden by the rulers, but they couldn't stop the thinking. A bit more than a century later, we saw the French Revolution, and the whole system everywhere was changed. And more recently, we have seen that kind of change after the world became corrupted by the concentrated wealth after the Industrial Revolution. And I'm talking about a bit more than a century ago. There are many examples where you see that humanity has looked at the situation, and despite the governing elite trying to prevent it, eventually big changes were made. So that again can happen on all kinds of scales. It can happen like just electric cars or capitalism as a whole, perhaps. So that is what I find interesting when it comes to positive tipping.
I didn't know you had a new book coming up. Now we've even broadened the topic, but we need to get to an end. What would you like the audience to remember from this conversation?
If you are a biodiversity platform, I would say you don't need to think about tipping points to decide to preserve biodiversity. I think that might be the most important message.
That was a great conversation, really very interesting and controversial. Thank you very much, Marten Scheffer, for joining Inside Biodiversity.
You're welcome.
If you have listened to this episode with Marten Scheffer and the previous one with Helmut Hillebrand, you've hopefully noticed a diversity of opinions on a contentious topic. That's not new for Inside Biodiversity. For instance, in episodes 6 and 7, you will find disagreement on what we should do about non-native species. In episodes 1 to 4, experts express different views on local biodiversity change. This is exactly what this podcast is about. We want to explore a range of viewpoints and challenge preconceived assumptions. And we hope you enjoy it. Email us at podcast@idiv.de for feedback, questions, or ideas.